Guys, we're going to get going the next session. Stateful Pre-Compiles. We've got Connor here. Give a nice little round of applause. Apparently, we've not been doing this yet. Nice little round of applause for Connor onto the dev bootcamp. A little bit during as well.
Thanks, Anthony. My name is Aaron, by the way, not Connor. This is Connor. Connor gave a talk earlier. Anthony just promised to say wonderful things about me for my introduction and then joked he would say horrible things. I guess it was something in between, which was get my name wrong. But thank you guys for coming. Today I'm going to be talking about customizing the EVM with stateful pre-compiles. Yeah, I love this little bit of let's build some cool shit. I usually put this on at hackathons. But if you guys have any questions or want to get really deep into the weeds, I'll be around after this, and I'll also be around tomorrow to answer any of your questions and get as deep in the weeds as you want, or potentially helping you guys build something. So as an introduction, I know this is a blockchain event, but I typically start out with what is a blockchain, what's a VM, and what's a subnet. This is a more or less technical talk, but I'm going to go through this anyway, so apologies if you already know what a VM and a subnet is. I'm going to skip the blockchain part because I think that's overkill for this. But all of you guys know what a blockchain is, and obviously each block defines some state transition for the network to perform. And so the piece that Avalanche uses is we define the virtual machine to be the semantics for that state transition. So in Bitcoin, that would basically define how do you transfer value, what is a transaction, how do you verify that that transaction is valid, and what state transition does that imply? How do you move funds from one place to another? And then, the next iteration is kind of Ethereum, where instead of just a simple transfer of value, you actually have the EVM, which is really defining a full semantics of Turing-complete smart contract programming language. So you can build anything and you can define that state transition to be whatever you want. So in Avalanche, this is what we define as the VM, and you can actually build your own and deploy it on a subnet. So that brings us to point number 3, which is what is a subnet? Hopefully you guys have had at least 3 people explain this to you this weekend, or even better if you guys have been in the community for a while, maybe you already know. But a subnet is essentially I'm going to explain this in a very technical way. It is the conjunction of a validator set and a set of blockchains that they choose to validate. So the first part of that is the validator set. If you create your own subnet, it is not validated by the primary network, the set of validators that are validating the XP and C chain on Avalanche. Instead, you actually have the ability to define your own validator set, define what weights they have, etc. And so that means that you define, let's say, which 10 validators, which node IDs are actually have a say in the network and what their say in the network is. The other part of a subnet is what blockchains are they actually validating. And a blockchain is essentially, at this level, it's essentially an instance of a VM. You can have the subnet EVM, you can have multiple different instances of it. So it's similar to an instance of a class versus a class itself. And so the subnet might be a single blockchain or it might be multiple. One example is the primary network, we sometimes call it the primary subnet, is the conjunction of the validator set for the primary network as well as the XP and C chain. So there are multiple chains on it. Yeah. Actually, I'm going to pause. Any questions on what is a VM or subnet? Great. So the next part is what is the subnet EVM? This is what we're going to be talking about today and how to customize it. The subnet EVM is the virtual machine that you use to deploy an EVM-based chain to your own subnet. So it's a fork of essentially CoreETH, the VM powering the C chain, and we've stripped out some of the excess functionality from CoreETH that we didn't want to deploy to subnets by default. So things like atomic transactions and some other modifications that we made that don't make sense for the subnet EVM if you're deploying your own chain. And on top of that, we've created some primitives for it to make it as easy to customize the subnet EVM as possible. So the principal one for this is Stateful Pre-Compile is the topic for the talk today. So to start out with, a stateful precompile builds on a notion that already exists within the EVM, which is the precompile itself. So precompile is a bit of a misnomer that has existed since the beginning. This is defined all the way in the Ethereum yellow paper. But essentially, it's a misnomer because it's not actually a contract that has already been compiled. You can't actually deploy an instance of the EVM that has a contract that's already been compiled and exists in the Genesis. This is actually very different from that, so it's a bit of a misnomer. It's actually Golang code that there is a system within the EVM to essentially pass off responsibilities to that precompile to execute some program on your behalf. So the way that I think about this is that it's a little bit like a system call. So if you guys are familiar with operating systems, sometimes what you do is there's some task that your user space program doesn't have the permissions to execute. So that might be interacting with the networking stack or the file system. And essentially what you end up having to do is make a system call that delegates that task and sends a request essentially to the operating system to fulfill some task for you. So this is very similar to that notion, where in the EVM it would be extremely expensive to perform some cryptographic operation because the EVM it's on top of this EVM interpreter, so it's just not ever going to be nearly as fast as if you were running executed or compiled code like in Golang. So we don't want to do these cryptographic operations on top of the EVM, on top of Solidity, because one, you're going to have to implement it in Solidity, which is going to be very difficult when we already have implementations of all of the cryptographic operations we might want in existing libraries. And we're just going to make it a lot faster. So the way that this works is you pass off this responsibility, and the precompile will essentially perform the cryptographic operation in the language that implements the EVM, and then spit out some output. So you can take a SHA-256 hash of any kind of byte string that you might have in Solidity, and this actually ends up in your code being based off of the keyword SHA-256. So if you're programming in Solidity, all you have to do is write SHA-256, and it'll take care of, under the hood, actually performing a call operation to the precompile's address. So the way that this works under the hood is that there's actually going to be one of the different call opcodes that invokes the precompile. So the call opcode is basically how you call their smart contracts, and it's in the exact same way, the way that you might call a precompile. So under the hood, when you write SHA-256, it's going to perform a call opcode, and you're going to essentially pass in an input data string, and then it's going to return some output in the same way that if you make a call to a smart contract, you're passing in some data that defines the call that you're trying to make, and it's going to return some data that is the result of the function. So a precompile in the EVM works the exact same way, and you also define the amount of gas that's required to perform the operation. So a stateful precompile is going to build on this exact same interface, and we'll see that in nav. So the whole idea of the stateful precompile is that precompiles are awesome. They give us a lot of great stuff, and they give us the ability to make things more efficient. But the reality is that they don't allow you to do all that much different things. And that's for a reason. You can't just create new precompiles if you're building on Ethereum or even if you're building on the Avalanche C chain. And the reason for that is you can't just go and say, hey, add this stateful precompile, it's going to optimize my smart contract, because you have to get every validator in the network to agree on what is out there, right? And so you can't just kind of force people to do that. And that would be a network upgrade that we need to get agreement on. We can do this if there's universal agreement on it, but it's not nearly as useful when you don't have the ability to really customize the instance of the EVM. And that's actually what subnets give us, really. So if you create your own subnet, then you're creating your own fork of subnet EVM, and then you can actually customize the code how you see fit. And what we're doing here is giving developers as powerful and as easy to use of a tool as possible to create custom iterations of subnet EVM that gives them whatever functionality they want, and integrates as seamlessly as possible with Solidity. So that's what this interface really is. And the only interface that actually gets exposed within the EVM when it's running the contract is it ends up just being that we're going to inject state access into the precompile. So now instead of just having an input string or an input byte string and then some data to return, we're actually going to give access to the EVM state, the caller address, the address of the precompile itself, the amount of gas that's been supplied to the operation, as well as whether or not the read-only flag is enabled. And once you have all of this information, you essentially have all the information that could be available in the EVM. And via this precompile accessible state interface, you can actually add in additional things that you might want to give it access to in the future. So this interface is really defined to give developers the dexterity to do literally whatever they want. And that's why devs, literally anything, is this a VM? And the answer is always yes. And the reason for that is that, Solidity and the EVM is already a Turing-complete programming language. You can build literally whatever program you want. It is all, anything you can build, anything you can build in Java, you can conceivably build in Solidity. But is that actually practical? Is that actually useful? Or is that going to be too slow and too expensive to make things actually work, right? The solution to this can really be stateful precompiles, because Solidity is always going to have this EVM interpreter overhead. It's going to have overhead from the Merkle trie. with this, if you have access to some external state and you have the ability to execute a program in Golang, it's sufficiently fast enough to actually build really whatever program you want and whatever functionality you want for a custom VM. You can just integrate it directly within the EVM while using whatever storage you want, anything else that you want, and still have access to use that Solidity interface so that you can build whatever application, whatever custom application that you want and kind of avoid those pieces of overhead. So if you're trying to build a custom VM, really the best place to start out with right now is the Subnet EVM. And if you're trying to build some application-specific use case, Stateful Pre-Compiles are really the best place to get started. So how does this work at the underlying level? What does this look like if you're a developer actually building a Stateful Pre-Compile? To understand this, first of what we're going to take a look at is the execution function for a Stateful Pre-Compile. And I've basically broken this down where you have the ability to implement different functionality in your Stateful Pre-Compile and basically mimic the exact same way that a Solidity smart contract might work to the very most granular level, which is if you have a Solidity smart contract, it is broken up into different functions that you might be able to call, as well as a fallback function that would be invoked if there's no input data to it at all, if you receive funds or something like that. And so we, in the exact same way, created this interface so that there is a fallback function that you can define. You can define how that function gets executed, so you can have that in the exact same way as if you're programming in Solidity. And in addition, we have function selectors, where basically it follows the exact same way that Solidity defines, based on the input data to a call, which function should actually be invoked. And so that's what is used in this functions map here, where we're actually going to take the first 4 bytes of the input to determine which execution function should actually be called. So there's first the fallback function, which if there's no input data, this gets invoked the same way that a fallback function would be invoked in a Solidity contract. And you can define all of the different functions you might want, and you can define what their function signature is as well. So you can basically say, this is the signature of this function, therefore this is the input data that should be mapped to it. And this allows you to say, you can define your function how you like and define the function selector for it, or in an easy way by just saying what the function signature is, and it'll be mapped immediately to that, so that those functions will be invoked when the user sends a contract call to it as if it were a Solidity interface. So what this ends up actually looking like at the base level, or at the user space level of interacting with the contract, is you can define each of these execution functions, define the program in Golang so that it'll be more efficient, define the fallback, etc. And each of those function signatures can actually correspond to one of these functions in Solidity, right? So you can define the keys and values that go into a prove function. You can define create trie to return an int. And you can do all of this stuff so that when the contract gets called, or if you call this interface, and you can do this from either Remix or from another smart contract actually programmed in Solidity, Solidity is actually going to know exactly how to interact with it from the very start. So what you would essentially do is you would define all of these functions in an interface in Solidity, and then on top of that you can actually define each of these execution functions in Golang. And so this ends up working out to be a really powerful way to say you can now actually call all of these functions as if you had built this entire thing in Solidity. And you can do this either in Remix, you can deploy this interface contract at a specific address, the Precompiles address in Remix, and then actually call those functions. So this is an interface for a trie or stateless storage. This is an idea that's been passed around in Ethereum as an interesting way to solve some storage problems in Ethereum. Not that many people are big fans of doing it at the actual level of the network, but the idea is essentially Ethereum has, and every EVM-based chain has, a whole Merkle trie, which stores the entire state of the chain, or at least most of the data aside from the blocks. But what you can actually do instead of that is potentially you can just store the Merkle root hash, and then anytime somebody wants to interact with the piece of the state, they would have to submit as well a Merkle proof of the data that they're interacting with. And so then you go from Ethereum nodes actually having to store the entire active state, which is potentially very large, to all they actually have to do is store a single 32-byte hash. And then when you move the requirement of where the data gets stored from each of the Ethereum nodes, which that ends up being very expensive, to the actual applications themselves. They would then have to keep track of their own state and say, okay, I made this contract call, now I can actually keep track of it. This is the only data that I care about. And you can actually use, by maintaining your own subsection of the Merkle tree, you can create Merkle proofs to say, this is the state I'm interacting with this in this call, and supply that at runtime. So then you can remove the need to have, you can remove the need for people to, or for Ethereum nodes to actually store that entire state. So this is something that would be completely impractical to implement in Solidity, but once you have stateful pre-compiles, you can actually borrow the Golang code that already exists to implement the Ethereum Merkle tree. And so what you could conceivably do is implement stateless storage at the smart contract level of basically creating a way to just provide a key value database that people can use, and then you can pretty much just implement this interface so that people can have this update, delete, commit functionality for a key value database all within Solidity. Now the question is, who's going to do that? And the answer is probably not me. I build the developer tools, and hopefully somebody here, if anybody's interested, I'd love to help anybody get started with this. I don't currently have time to do this, but this is in every single one of my presentations because it's trying to inspire people to build cool stuff, and this is what I personally think would be really cool to see. Thank you guys for coming. Yeah. And now let's see. Yeah, I think there's a little bit of time for questions. Does anybody have any questions?
Yeah, just when you were introducing, I was wondering about the bridging capabilities between the subnet and then the main chains. You didn't talk about that, so I was just wondering there must be I was thinking there must be a good channel to do that, right? Because why would you otherwise do a subnet in the first place?
Good question. So yeah, we have cross-subnet transactions on our roadmap in the future. Currently, that's not supported. So the subnets that have been spun up, they've created their own bridges in the same way that you would bridge between Avalanche and Ethereum. They've created similar bridges between the Avalanche primary network and their subnets. This is obviously not ideal, like you said, but we do have cross-subnet transactions in a pretty clear way of how that's going to be implemented in the future. It's not fully spec'd out yet, but when we have that, then that will kind of create it so that instead of just having a subnet that is really its own network, you will have the ability to create a subnet. One, it's very easy to do so on Avalanche. It's very straightforward to set it up. And two, you will be immediately connected to the rest of the Avalanche ecosystem. So you're right, that is a huge part of the value add, and it's not there yet, but it is coming.
Yeah, can I follow up on that?
Sure.
So then I don't really get, if I do a subnet, or I just take that and run it not as a subnet, what's the difference in it?
Sorry, are you saying what's the difference between taking Avalanche Go and running it as your own network as opposed to? Yeah, not a huge amount right now, because it is, there is no cross-subnet transactions. So the real difference would be whether or not it's connected to the ecosystem in the future. From a usability perspective, it's really, once we have that functionality out there, you would then be running a network that is isolated from the rest of the ecosystem. Whereas if you launch a subnet now and subnet transaction or cross-subnet transactions are released 3 months from now, then suddenly everyone that decided to release on an Avalanche subnet is immediately connected and they can get rid of their bridges. And because it's going to be natively integrated, cross-subnet transactions will most likely be significantly more secure than most bridging solutions. Obviously, there have been a large number of bridge hacks. Bridges at the fundamental level are going to be a little bit less secure than things that are natively implemented. So you would kind of be stuck in that solution. And you could spin up a subnet at that point once that's there, once that's a sufficient value add. But you're right in that there's a significant piece of the value out of subnets, that interconnectivity between them, that's not there yet until we have cross-subnet transactions. Does that answer your question? Yeah. I think the answer that you're looking for, I can give you in 3 months, hopefully.
I have a network right now that is external, and I'm thinking about turning it into a subnet because I have all this amount of code that I really don't want to take care of anymore. But the protocol is not really clear to me, so I wanted to understand what that actually is. But it seems it's not a whole lot. That's what I'm getting.
You're saying what's the value out of switching from running your own network, which you're doing now, to
what the interface is in order for it to be a subnet? What's the link actually to be a subnet?
What's the link to be a subnet? Oh, so a subnet is it's a concept that exists natively within Avalanche. So on the primary network, we have the X, P, and C chains, and so the P chain or platform chain is the one that takes care of all staking logic. So a lot of other chains, they've done this thing where staking logic is actually implemented in some smart contract and does some things. We've actually created a completely separate chain to isolate this logic and keep it separate. So the platform chain is where all of this would happen, where one, you add validators to the primary network, and two, you also have the capability to then add validators to a specific subnet, to create a subnet, and the P chain actually orchestrates the creation of that. Is that what you're...
The state roots are somehow entered back into the chain, or what?
Sorry, I didn't catch that. Could you repeat that?
The state roots of the subnet are then like anchored in the P chain or something?
No. That's an approach that a lot of other people take with some of their chains, but a subnet is actually completely isolated. So that's part of this debate about, shared security or state roots being posted to the original chain. A subnet is actually, like you said, it's very much like an external network. There's no connection where the state roots of it are actually posted back to the P chain or anything like that. In fact, a VM is not required by any means to have state roots at all. The X chain doesn't have a state root. It's only actually the EVM, subnet EVM, that even has a state root.
Can you have validators that are shared between multiple subnets?
Yes. The requirement for a subnet validator is that you validate the primary network as well. So in order to be added as a validator for an additional subnet, all that you have to do is be a validator on the primary network, and you can actually be added to an arbitrary number of different subnets. The caveat to this is that validating an additional subnet comes with the overhead of actually validating that chain. And so if you try to validate 100 different subnets on a toaster or something like that, you might not actually have the capacity on your machine to perform that validation correctly and well. And so you might not get the rewards that come with that. You might run a node that can't actually scale to that. If you decide to run an extremely beefy machine, you might be able to scale it to something significantly larger, but it's going to be dependent on the node itself. Are you running on an extremely large instance, or are you running on something very small? The number of subnets that you can actually handle. And that's kind of a part of the promise of subnets, is that you can actually have this be separate logic, so that you can have some nodes that are validating this subnet and other nodes that are validating a different one, so that you can have all of these subnets that maintain their own state, and you don't have to keep all of the logic on all of the different nodes. So it's similar, it's essentially sharding the state of all these different chains among a different validator set, so that you don't have to have one validator that's validating the entire network of every subnet that's ever created. Cool. Thank you guys so much for coming.